Hello Year 10, your first job for this week's remote learning is going to be a rapid recall task. So you need to get yourself some kind of song, pick AC/DC because they're good and topical. If you don't want to pick AC/DC, you don't have to, I guess, but I might think a little bit less of you. I'd go Back in Black, there'll be a link in the description, but some song that's 4 to 5 minutes long, ready for the next page. So pause the video here and get yourself a song ready. Okay, hopefully you have your song ready for the next page. It's going to be your time limit for these questions. You need to draw the symbols for a diode, thermistor, resistor, LDR and variable resistor. You need to sketch the IV graph of a bulb, a resistor and a diode. So a current voltage, current potential difference graph. You need to sketch a simple series circuit with 2 bulbs and an ammeter. You need to add a voltmeter, measure the voltage of both bulbs. You need to write down 2 equations, bonus points if you put down the units, for calculating power, and you need to list 1 safety feature of a British plug. Oh, extra S there, but there we go. So pause the video here, play a song and see how we get on. Okay, so answers time. Here are my symbols for a diode, thermistor, LDR resistor and variable resistor. We've got the IV graphs here. You want to have a straight line going through the origin for a resistor. You want to have a curved line either side for a bulb. Doesn't obey Ohm's law. It's a curved line. It's not directly proportional. This is directly proportional. For a diode, you want to have it flat against the zero current graph here. Okay, so it's 0 current until it gets to this positive value for potential difference, and then it starts to increase. Here's my series circuit with 2 bulbs and ammeter, and here's the voltmeter drawn in parallel around those 2. Now your ammeter can be placed here, here or here in the circuit because the current's the same everywhere. The voltmeter, one edge has to be on either side of the 2 bulbs. Here are 3 equations for power. Power is energy times time, power is current times potential difference, and power is current squared times resistance. You can have the symbol equation or the word equation, either is fine. Any sensible safety feature of a plug, so earth wires, fuses, earth pin being the longest, cladding on the live and neutral pins, the cable grip, earth wire being longer than the others, so it's the last to be pulled out if the cable gets tugged. Any sensible safety feature would be good. Okay, so hopefully you did okay with that. We're moving on from electricity. Okay, now I'm going to put out another video just as a recap of that electricity topic, and I'm going to include in that just a little bit of conversation about where we're at in terms of the syllabus. And we're in a really good position at the moment, Year 10. We're, even with this crazy lockdown, we're doing really quite well. We're missing some practical work. Okay, some of the core practicals you'll need to get some more experience in, but for the most part, in terms of theory, we're really on it. We're really doing very well. So having said that, we're moving on from electricity onto something new. So you need to get yourself a pen and a pencil, or a pencil and some paper, something to draw on for the next slide. So if you haven't got those ready, pause the video here. Probably get all your stuff ready now if you haven't already. So pens, pencils, something to draw on, all that kind of stuff. So first job, I want you to just sketch really roughly what does an atom look like, and start thinking about how do we know that? How do we know that the atom looks like that? Why is it important? So pause the video here, spend 60 seconds, max, maybe 2 minutes if you're a slow drawer. Just sketch what an atom looks like. What do you think an atom looks like? Think chemistry. You've drawn them lots and lots before. Okay, so pause the video here, give me that sketch. Okay, now a lot of you would have drawn something like this, where we've got the neutrons and protons in the middle, in the nucleus, and we've got electrons orbiting in these circles. Okay, negative electrons, positive protons. If you put that as positive, give yourself some brownie points, give yourself a little pat on the back, and neutral neutrons. Okay, this is the picture of the atom that you need to know about, especially for your chemistry. Okay, but you might have drawn something different. You might have drawn something like this, where we've kind of tried to draw the electrons going in 3D. If you're really clever, and you've already done your GCSE and your A-levels, you might have drawn something that looks like this, much more complicated, or like this. Okay, these are all different models of the atom. Okay, and we didn't just come up with them from nothing. Okay, it developed over thousands of years. Okay, this is the one that you use the most. Okay, and you use it the most, and we use it in GCSEs because it's a really, really good model to explain lots and lots of different parts of chemistry. Okay, knowing where the electrons are in these shells, knowing how many protons and neutrons are in the nucleus, knowing the distance, how far out the electrons are in these shells, all of these things can tell us about how reactive an atom would be, and the number of electrons can tell us what kinds of other atoms it will react with. Because chemistry is all about these electrons sharing and moving, and how these electrons interact in different atoms. Okay, so this is a really, really, really good model for chemistry. It's really, really powerful. But it's wrong for other things. Okay, it's not a perfect model. It's not how we understand what the real, or closer to the real picture of what an atom might really look like. Okay, but it's an incredibly powerful tool, this model, in terms of our chemistry. Now, there's massive overlaps in this topic between chemistry and physics. Huge. Okay, in chemistry, you are going to learn about, in slightly different ways, the history of the atom, how that changed over time. Okay, but chemistry is more about making and breaking bonds and what happens to the electrons. The physics is a little bit more focused on what's happening inside the atom. Not entirely, but that's where the focus will lie, what's happening inside the nucleus. And in this atomic structure unit, where we're going to be learning about radiation and radioactivity, we need a grasp on how we got to the picture we've arrived at, okay, to help us understand what's going on. Okay, so here is a timeline. Here's an example of a timeline of that model. Okay, and we start off thousands of years ago with Democritus, who came up with this idea of the atom, that if he took some chunk of material, some big block of cheese, and he cut it in half, and he kept on cutting it in half, and in half, and in half, and in half, over and over and over again, he'd eventually get to a small enough bit of cheese, or whatever the material was, that you couldn't cut it anymore. It was no longer divisible, it was indivisible, it wasn't cuttable. And he came up with this word of atomos, which means uncuttable. Okay, and that's where we get the word atom from. So he was the first person to really think about atoms and what their material is up with. And he was able to link it to theory. He was able to link it to practical, to experimental results. You know, he thought that the material that these were made from might have different surfaces. So solids might have kind of a rough surface that would join together, whereas air atoms would be much smoother, so they could flow over each other. So it was linked to science in a way. Dalton came along much later, and he developed some really important work in chemistry in how these atoms can interact and why they form different chemical compounds in different ratios, and his ideas were really important for chemistry, but his model was just really simple, different spheres. Okay, different spheres making up these atoms. Thomson, okay, he showed that he discovered the electron, okay, and he had developed this model that's called the Plum pudding model that we're going to talk about in a little bit as well. Rutherford expanded on it and changed it into this nuclear model. Bohr developed these rings, these energy levels. Chadwick discovered the neutron, and then in modern days we've developed it even further. Okay, now in terms of your GCSE physics, you really focus on Thomson, Rutherford and Bohr. Okay, you need to know about Dalton and Democritus, and you need to know about Chadwick, but this is the real focus of the model. How we go from the older examples of the structure of the atom to the ones that we actually use in our science in your chemistry lessons. Okay, now you're going to be developing your own timeline. That's what your task is going to be. Now I'm going to focus on talking about Thomson and Rutherford because I think this is the most important sections that you really need to understand, and I also think it's the most confusing. So I'm going to be focusing on the next few slides about these. Okay, in your research, you're going to have to find out about Democritus and about Dalton and a little bit about Chadwick. Okay, focus your research on Bohr and what he did with flame tests and energy levels and discovering these different circles. Okay, so I'm going to talk about these three. Okay, one of the things that students get hung up on and get confused by is the fact that it's called a plum pudding model. Okay, now the Victorians are a little bit odd, and they had the same name for plums as raisins, so they call raisins plums. And a plum pudding is like a Christmas pudding, where there's raisins inside this bit of kind of spongy bits. Okay, a more modern way of thinking about it might be a chocolate chip muffin. Okay, now this idea that Thomson came up with was because he discovered the electron. Okay, and he changed the model from Dalton, these spheres, these atoms that were spheres, to be a positive sponge with little negative electrons embedded in it, where the sponge is like the sponge of the chocolate chip muffin, and the electrons are the chocolate chips. Okay, and it was a good model. It fits all of the experimental data they had up until the next guy comes along. Okay, it was consistent. All of these experiments were consistent with chemistry. It could predict, it could be used to predict reactions. It explained static electricity, did all these things. So we're putting here, the model of the atom was consistent with all the experiments in chemistry and the new area of static electricity, where this electron comes into play. This positive dough, okay, with a negative electron stuck inside it. Solids can't be compressed, so the atom must therefore also be solid. So this bit is solid. Okay, rubbing the two solids together can move about the electrons. Okay, so these things can move between the different atoms. So it explains the idea of static electricity. Okay, so it was a good model. It worked really well. Okay, and you need to know this diagram, and you need to know that it supports these different parts. Okay, now the next discovery, okay, was a wonderful bit of science. Okay, now this chap on the right is Rutherford, and on the left you've got Geiger. Geiger you might have heard of from Geiger counters. Okay, now Rutherford was doing lots of work in radiation. Okay, he was one of the first people to really investigate alpha radiation and beta radiation. Okay, and did lots and lots of different things. And he's famed for this gold leaf experiment. In reality, Geiger designed the experiment, and Geiger and Marsden collected the results from various experiments. But it was Rutherford who had a little moment of genius to slightly change the experiment. Okay, and they got some strange results. And strange results can be the most exciting. Okay, so this is a simplified picture of the equipment. So you can see it somewhat here. But here's a simplified picture. We've got this alpha particle source. Now you can learn more about what alpha particles are in the radiation unit, but the short version is it's a radioactive particle. It's made up of 2 protons and 2 neutrons. Okay, and Rutherford was using these, okay, to probe the inside of the atom. Okay, and they were projecting these alpha particles through really thin films of metal. Okay, gold being the most famous. Okay, but they did other metals as well, but gold's the most famous. And they got unexpected results. Now, unexpected results in science are the best. It's when science gets interesting. It's when you have to change your models, you have to change your understanding. Okay. Now, the plum pudding model, okay, Thomson's view projected this, that most of the alpha particles will just go straight through the gold film, and a few of them, a tiny amount of them, might be deflected by a very small amount. Okay, but for the most part, they just go straight through, not being really deflected much at all. Okay, but what actually happened was the vast majority went straight through, but some were deflected by quite, sizable angles, some by very large angles, and some even went backwards. Okay. Now, it was not a pleasant experiment to take results from. So if you look at the bit of kit here, this is a little telescope that moves around around the system, and Marsden or Geiger would sit there for hours counting every time an alpha particle went down this tube and had a tiny little flash on this fluorescent screen, like an old television screen. And it took a long time to get the results. It was difficult experiments, and it seems a bit of a shame that they don't get as much recognition as maybe they should. But it was a fantastic experiment because of this result, they knew they had to change this model, and they changed it to this one. And there are 3 reasons why they did that, and you need to know them. Okay, so the results. Most of the alpha particles go straight through. Okay, that tells us that most of the foil is empty space. That's the first result and the first conclusion. Most go straight through, most of the atom is empty, most of the atom is nothing. A small number of alpha particles, okay, were deflected by large angles, so bigger than 4 degrees. Okay, that's when the alpha particle goes close to a nuclei. Okay, so if a small number are deflected at large angles, that tells us there is a concentration of positive charge in the atom, because similar charges repel. Okay, the alpha particles are repelled a little bit by the positive nucleus. A very small number of alpha particles go straight back off of the film, deflected by extreme angles. Okay, that tells us that the positive charge and mass are concentrated in a tiny, tiny volume, the nucleus. Okay, because there are so few of them bouncing back, the chance of this type of collision is very, very small. Okay, so those are the 3 results that you need to know and the conclusions that go with it. So based on this, we change our model of the atom to look like that one that's a little bit more familiar to you. Okay, so your task is to do some research. Now, like I said, you need to really focus a lot of your research on Bohr and what he did to change that model. Okay, because I've talked about Thomson and Rutherford, you need to find out some information about Bohr and these energy levels. Okay, and then if you have time, add some other bits of information about Chadwick and Dalton and some Democritus. But this is your focus. So you want your own timeline, and it has to include Democritus, J.J. Thomson, Rutherford, Geiger and Marsden, Bohr's orbital ideas. Okay, this is what you have to include. Diagrams are really important. So you need to have some diagram of the Plum pudding model, some diagram of the gold leaf experiment, some diagram of Rutherford, and some diagram of Bohr's models of the atom. Pictures are 1,000 words. Okay, so label diagrams can be really, really important. Okay, dates, people, other key facts would also be really good to see, but the diagrams are the key bits. And you also want to have your own little idea of these results and conclusions that Rutherford, Geiger and Marsden got to. Now, along with this video, I'm also going to put up some other slides that can help you with your research. Okay, and that's going to be attached to the class charts. You want to spend, because this is now the best part of 20 minutes of YouTube, you want to spend maybe 40 minutes on making this timeline. No more than 2 big spaced out pages of work. Okay, so that's with big diagrams and short sentences. Okay, I hope you're all doing well at home. I hope you had a wonderful half term. I hope you enjoyed the fantastic weather that we certainly got at the beginning. I'm not sure if we've got to, I've recorded this video early, so I don't know if the latter part of the weather is going to be good or not, but I hope you had a fantastic half term. Take care, and I'm sure I'll see you soon. Bye bye.